Just a little bit of housekeeping today. I want to make sure that everybody's aware. The whole session today is about an hour. We've got it divided up into 3 different sections. Long fiber thermoplastic composites. We'll talk about what is long fiber. We'll talk about the performance benefits. We'll concentrate on 2 of the most common fibers, glass and carbon. And then we'll talk about the market-driven specialty technologies that we've actually created also, as far as in response to the marketplace. Then we'll turn it over to Mark Henry, and he'll talk about designing for long fiber composites, and then we'll wrap it up with a Q&A session. Let's take a look at thermoplastic composites themselves. And we talked about earlier, questions. We do want questions for the Q&A. We're talking specifically about thermoplastics. Certainly, I think a lot of you are familiar with also thermal sets. I expect that to be a question that we get asked as far as what the difference. So now's a great time to capture that question so that we've got that afterwards. But let's talk about thermoplastic composites. These are melt processable thermoplastic polymers as the matrix with a fiber reinforcement component. They're commonly processed through injection molding methods, but they're also formable in profile extrusion as well as compression molding. When you take a look at fiber reinforced plastics, what that really does is it's really expanded the plastic performance envelope for designers. And when you take a look at reinforcement options, you're looking primarily at particulate fillers, you're looking at short or chopped fiber, you're looking at long fiber, which has really the best performance obtainable with injection molding compatible materials and matrices. And also continuous fiber in fabric mesh prepregs. Those are really the 4 major ways that polymer matrices get reinforced. Common fiber types, just in general, they range from metal to natural. And really, as we mentioned earlier, carbon and glass are the most commonly found. In concentrating on long fiber's uniqueness, when you take a look at long fiber and compared to short fiber, one of the things that is unique, and this is another great one, we're not going to spend time of it here, but it should be a question. When we look at long fiber composites, it's really through a pultrusion manufacturing process. You're looking at a cut pellet of around 12 millimeters, ½ inch in length. And the fibers are unidirectional. They're all in one particular direction. And you're looking at starting out with a 12 millimeter pellet, and through injection molding, just because of the process itself, you're looking at a fiber that has a length probably around a mean of 3 to 4 millimeters and a distribution off of that. One of the key things here is that high fiber aspect ratio. Length to diameter ratio. That's where the unique performance comes in. Again, the longer the fiber, smaller the diameter. That's where a lot of the uniqueness of a long fiber type of reinforced plastic comes in. You take a look also at short fiber, and in short fiber, I think the critical thing here is, just naturally you have, as you might expect, you don't have really the aspect ratio that you do in long fiber. That's what makes long fiber unique. You may start off with a pellet that has a fiber of about 1 millimeter in length versus 12, and then finally through the processing and an injection molding machine, you may end up with a mean of considerably less than 1 millimeter and a distribution off of each end. From a pultrusion process standpoint, won't spend a lot of time here, but again, this is a great place to capture a question. Are there any other methods for making a long fiber product? That's one that we can tackle during the Q&A session. What we concentrate on is what we know the best is the pultrusion method. And again, you're looking at anywhere from 2,000 to 24,000 ends of a unidirectional fiber in that pellet. And it's our goal, it's our real objective is to make sure that we've got We've got polymer matrix around every one of those fibers, minimizing voids, which detracts from performance properties. Now let's talk about long fiber performance benefits. There's a lot of them. I'm going to go pretty quickly here, but again, you will have access to this presentation afterwards. Certainly, stiffness and modulus is a critical long fiber benefit. Strength in load carrying capability is another absolute long fiber benefit. Toughness and impact resistance is another one. And again, what many people find is that it's unobtainable through other methods of reinforcing plastics, and that a fiber network picks up stress and energy and distributes over a wider area throughout the component. And I think one of the things that really points that out, I'm not going to spend a lot of time here on this particular graph, but stiffness, strength, and toughness. If you're really looking for stiffness, certainly you might be able to get that with short fiber, but it's those applications where you're looking at increased strength and toughness. That's where long fiber comes in and shines. One of the things that I really like in this particular slide, you see the part on the left. You see the part through pyrolysis, where we have burned off the matrix and left only the glass network. And what you can see there is we are, in fact, with long fiber, when you use long fiber, you're setting up a fiber network that is incredibly dense and provides that semi-structural and structural integrity that you can't get with other types of reinforced polymer. Some more long fiber benefits, and this is one of the key, and that's mass reduction and lightweighting. Certainly that's why LFT has had such a penetration into the automobile market and transportation market over the last couple of decades. Dimensional stability, better creep resistance, consistency in holding tolerances, low coefficient of thermal expansion. And again, reflecting back on that last slide where we saw the network, the fiber network, I think it becomes pretty natural as far as an understanding that on why that happens. Cyclical fatigue endurance, vibration and sound dampening, reprocessing and recycling through remelting. Those are again some of the real attributes here given to long fiber. The other one, of course, is metal substitution. And, no question about that. It's one of the things that so many people, when they look at long fiber, it is the go-to product, go-to material for metal replacement, or actually when other plastics fail. Again, high strength-to-weight ratio, ease of forming and manufacturing components. I hate saying this, but because we've converted a lot of metals to composites, but we've been working with metals since the Bronze Age, and so there is an incredible comfortable feeling about working with metals when you step off and you take a look at a different material. Really what we do is we're offering designers and folks out there that are using metal to actually optimize from a cost standpoint and a weight standpoint. So it may feel a little odd, but in a lot of cases metals are over-engineered. And so this is another way for designers and companies to optimize their material selection. I think the other thing that's important here is we encourage people to look beyond just the pure cost per pound of material. I mean, evaluate the entire system of cost of manufacturing components. I mean, we've had people, be able to reduce the finishing costs that they have in metal and things like that by actually, part consolidation, molding different features in that normally what they had to do was to fasten or screw or bolt or something like that. I mean, take a look at the entire system. That's critical. And then just a couple of other things. Plastics provide, long fiber plastics provide more design freedom and versatility. We've talked about that. They also provide corrosion resistance, electrical and thermal isolation, and radiolucency. And I think just a little bit more about metal conversion qualification. Certainly, whoever you work with, if you're deciding to go with LFT, it is absolutely critical for you to find a team out there, somebody who's working with LFT that has the ability to sit you down if you're doing that conversion from metal and run you through the critical questions, typical and maximum loads, the length of time under load, operating temperatures, chemical and or radiation exposure. Absolutely critical from the standpoint of making sure that you're working with a team that will critically take a look at your application and help you walk through it. Sometimes, and we've had this happen, you take a look at metal conversion and it's just not a fit. They can't get there. That happens, and certainly working with a team that has the honesty and the candidness to tell you that up front can save everybody a lot of issues. Certainly economic benefits from conversion, those are certainly things to look at. The ability to optimize design for new material, again, another consideration in conversion qualification, because I'm going to be totally upfront with you. Rarely have we found plastics to be a successful drop-in, just a drop-in substitute for metal. I've got a part that looks like this and it's in metal, and I want to make it in plastic. There are certain things that have to be considered from a design standpoint in order to cross that conversion bridge. Make sure that you're working with somebody from an LFT standpoint that understands what that takes. And also, more importantly, last bullet on the page here, and that is, has the portfolio of simulation tools to predict reinforced plastic behavior and design feasibility. So now let's talk about the fibers. Again, we're going to focus only on the two most common. One is glass. We'll cover that first, and we'll talk about carbon fiber. Certainly, long glass polypropylene fibers, they've been around for, my God, decades, over 30 years. So there is a really good track record of metal substitution success. When you take a look at glass in itself, it's strong, yet it is flexible. And certainly it makes a great reinforcement for a whole range of thermoplastic materials. This graph kind of says it all. This spider map here, we call it the performance trifecta. Focus for a second on the red line. That's our PA66 50% loaded by weight glass. It's also our MT, which is where we have added some additional toughness to the resin in interfacial here to produce this. But again, against this particular map, I think it's rather obvious. Again, there may be some questions that you have. Let's talk about them in the Q&A. But again, this is why we feel pretty strongly about glass as a reinforcing fiber. Actually, it gets pretty well reinforced on this chart too. I'm not going to spend any time on it. The numbers, when you take a look at neat polypropylene or neat PA66, and you take a look at the performance improvement with a long glass fiber, 50% by weight in polypropylene or nylon, take a look at those numbers. I mean, those deltas are incredible, and certainly those are the kind of things that an LFT product can do for you. I'm not going to spend a lot of time here. It's the red bars. It's the red bars. Long fiber is significantly tougher than short fiber. Lightweight metal options and long fiber skeletal fiber network. Remember that one slide that we had way back where we had burned off the matrix. Continues to boost durability as fiber content increases. And again, I keep going back to the aspect ratio. That length and diameter aspect ratio here, starting with that 12 millimeter pellet, starting with that type of aspect ratio helps produce these kind of results. Couple of applications real quick. What we're really trying to demonstrate here, and it's also, I'm sure it's going to come up in Q&A, what kind of geometric, since this is a long fiber product, what kind of complex geometries can you get into? And these are really good examples of what we've been able to do with glass, long glass fiber. Now let's talk about carbon fiber for a second. One of the critical things, it's been widely adopted in aerospace, defense, sports, and recreation for decades. It has a high-tech perception, no doubt about it. One of the things that certainly has prohibited a lot of carbon penetration in the reinforced polymer area has been certainly the steep cost. When you take a look at glass compared to carbon fiber, we always get the question, well, how much of a difference is there? And it can be over a multiple of 10 times as far as the difference between glass, cost of glass, and cost of fiber. So certainly carbon fiber. So you are looking for those applications, certainly from a metal standpoint. When you're looking at metal replacement and conversion, carbon fiber becomes critical. But that cost entry barrier has to be hurdled. And it's also electrically active. And you're going to get black as a color, versus in glass you can do different colors. From a long carbon fiber standpoint, I think one other thing that's important, take a look at, top choice for mass reduction and lightweighting. 30% lighter than glass, 50% lighter than aluminum. And I think the other thing is, a lot of people ask, well, why is glass and carbon so different? And I'm just going to go back to aspect ratio here for a second. The diameter, and again, think about the pellets, the 12 millimeters in length. Well, the diameter is actually on carbon fiber 1/2 that of glass. So again, from an aspect ratio has gone up, your performance has gone up. That's maybe, it probably is too simple of an explanation, but I'm a simple man. So anyway, that's carbon fiber, but you can see here in the reduction of weights and densities. And again, not to spend a lot of time on the chart, but again, versus a neat resin, look at some of those deltas as far as in polypropylene and nylon. And again, back to performance boost chart, the red bars, that's the carbon fiber product. In the lower right, you also see the comparison with metals. Certainly, every application is different if you're looking at a metal conversion, and that's why, again, if you're working and you're looking at LFT composites, make sure that you're working with a team that, in fact, has the ability to help you through that and make a judgment call. Again, carbon fiber, so we are not afraid, the industry is not afraid of complex geometries. Certainly they can be done with a long fiber product. Now let's take a look at some market-driven types of changes that have happened as far as from a technology standpoint. I think one thing that's really important to point out, now I'm going to be talking about plastic comp a little bit. When you take a look at plastic comp and why we feel that we're a little bit unique, why the marketplace says we're unique, is that we are 100% focused on long fiber. There's companies out there that have their own chemistries. There's people that have their own, they do short fiber, they do compounding, they do different types of polymers, different types of fibers. We're pretty focused. We are focused on long fiber reinforcement. And when you take a look at our expertise, we actually go back over 40 years in the focus of long fiber. We have products, we have tailor-made products, to meet performance specifications. Literally, and we're proud of, we can take any resin from polypropylene to PEEK. We can take any fiber, glass, carbon, basalt, aramid, stainless, and we have experience in making those work in a long fiber type of product. And then certainly we have the compounding capability of being multifunctional by adding conductivity, lubricity, flame retardant, color. The other thing that I think makes us unique, if you look at our customer list, and we have, my God, over 400 and some customers on our list, but the majority of them, we share a partnership philosophy, and I know that's overworked, but I think combined with the last bullet here, which is being able to go vertical, meaning that we have the capability in long fiber, and we feel it's one of the best in the world, of being able to go from design all the way to helping process the product. And everything in between, which means certainly the analysis, certainly the compounding, as well as the design function. We can go vertical from design all the way through to the final processing. So pretty important and also pretty unique. Now let's talk about some of those unique market-driven technologies that customers came to us, and one of the things they questioned. Remember, we talked a little bit about the carbon cost barriers. We came out with a product called, it's a hybrid. It's glass in carbon fiber, again providing the stiffness and the benefits of carbon, as well as providing the impact difference, the improvement as far as in having a glass fiber within there. Very unique. Again, not going to spend a lot of time on that. Let's share that in question answers here in a little while. Customers came to us again. Marketplace came to us. Can you improve the toughness of, we have a matrix issue. We want something that's tougher to go with the LFT toughness, and we came up with a product that's has a 400% increase in toughness over short fiber compounds. Again, marketplace driven. And you can take a look at the impact comparisons there utilizing that product. Another marketplace came to us and they said, hey, what can you do about appearance and color? And what can you do as far as, we're pushing long fiber around the tool. Can you give us a greater productivity in being able to use that? Can you get us into thinner walls? And we came up with a product called Velocity, which, again, as you can see here, increased flow length by 30%, cut injection pressure by 40%, reduce cycle times by 25%, lower molding temperatures, and take a look at the pictures there, a significant improvement in appearance. And we even had the marketplace come to us and they said, hey, you got long fiber, but can we see through it? I know that seems crazy, but you know what? We did it. And we actually came up with, that is, believe it or not, in that photograph, that is a long fiber product, and you can actually, it does have translucency. Again, those are the different things, from we can also compound in wear resistance, electrical, flame retardant, and appearance. And from a material review standpoint, we've talked about long fiber, certainly the highest level of structural performance available in injection molding. And certainly we have the capabilities as a single supplier to support you from concept through production. I want to thank you for that. Now I'm going to turn it over to Mark Henry, and he's going to talk about design with LFT. Thank you.
Thanks, Greg. Okay. So, as Greg said, you rarely just want to drop in a different material in a previous part's design. So, because of that, we like to look at 3 different factors right when we're starting out the design process. We want to look at the injection molding process itself. That means you want to keep in mind the mold and how material might flow through it and what the challenges there could be. You want to think about the material itself, long fiber specifically as we're talking about it today. And what gains can you get from using long fiber over an unfilled resin, over an aluminum, over a short fiber? There are so many materials to pick in the workplace now. So you want to think about the material. And then you want to think about the part and tool design. So now, is your part molding friendly? Is there a way to make it more molding friendly? Or maybe compression molding? There's a lot of ways to process that design as well. So keep in mind, you don't want to just drop your old part in and then with a new material and expect it to behave the same exact way. So going deeper, here are a few things a little bit more specifically that you want to keep in mind at the forefront of your project. You want to think about the fiber content that you want to use. We typically range from 20 to 50% by weight. Now the reason for that is anything below 20%, you're not getting a whole lot out of your bang for your buck on that point. It's still going to be flexible, won't be as stiff as you're looking for, maybe not as durable. Anything above 50%, you start having an issue with the resin matrix accepting the fiber. And then you start getting a little bit more of a brittle behavior, and it doesn't actually strengthen the part very much. You might get additional stiffness, but overall it won't be as tough if you go above 50%. Then you want to think about your forming process. Are you using injection molding, compression molding, sheet molding? There's a lot of strategies there. So you want to make sure your geometry will be friendly for that scenario. You want to think about fiber chemistry. What kind of fibers are you going to use? There aren't just carbon fibers and glass fibers. There's different grades of each. And it helps to have somebody on your side that knows the different kinds of fibers that can help you out in selecting that correctly for your product. You also want to think about fiber morphology. Now, when I say you think about it, I mean more like we're going to think about that for you, because that's the tricky chemistry part about what sizing you want to put or what kind of coating you want on those fibers so that the fiber itself can bond better to the resin matrix. We'll handle that part for you. You want to think about fiber orientation. This definitely matters, similar to the concept of you want to pull on a rope instead of push on a rope. This is where you want to start aligning your fibers in the highly stressed regions of your product. And you want to think about your fiber length. Is this something where you can have a short fiber, where you can afford that brittleness, or do you want to go with something tougher? Do you need to go with something tougher? It's good to keep in mind. Now, here are 3 products that I like to use to describe some of the ways that long fiber can benefit a product. On the top left, we have a crossbow riser that's loaded over 1,800 pounds during testing. Now, this is the most structural component of the crossbow, so it's responsible for handling a lot of load. So we need to ensure that it's going to be tough, and tough over years, and tough in several environments. And so that part was very successful in the archery industry, because it also lightweighted the aluminum predecessor significantly so that people can carry it further without getting fatigued. On the bottom left, you actually have a component that's used on planes and any airlines. Now, this was used to space out the seats, provide an armrest, but as you know, when it comes to airlines, there's a lot of robust testing that needs to take place for a component to get accepted, and this component was accepted. And another reason why it was is because of the amount of lightweighting it was able to achieve. When you're dealing with hundreds of seats, this saves a lot of dollars in fuel. I also like this component because you can see all the geometric intricacies. You're able to put ribs and structural geometries in places that, maybe you wouldn't be able to do with a layup process, or machining would be too costly to do so. So here we can get strength where we need it and not where we don't. So we can save money in that strategy as well. On the far right, you see a component that was used in a cell phone to hold the components in place. Now, it needed to be tough, it needed to be thin-walled, and it also needed to provide some EMI shielding so that the electrical components don't interfere with each other. Now, when you're switching from metal replacement into composites, here's a few perks that you want to think about and what might cause you to switch materials. And one is that long fiber actually retains geometric dimensional stability under loading quite well. In other words, simply put, it's very stiff. Now, another way that also helps is because when somebody may gouge a surface, it's harder to gouge deeply because you have long fibers holding that material in place. So in that way, it's scratch resistant. Also, you want to think about the low weight to high strength ratio. The reason a lot of people use aluminum is because they want to go lighter weight. And we're actually 40 to 50% lighter than that using long carbon fiber. I also recently did another calculation to compare with magnesium, and the long fiber was actually 18% lighter than magnesium. So if you're looking for that cutting edge over, let's say, the rest of the market, this is where you want to go. Also, when you're looking at molded-in intricacy, I know as a designer myself, I appreciate the ability to just put in a fillet or put in a stress-reducing geometry or ribs without having to worry about the machining costs that might entail. So it gives me a lot of freedom as a designer. I can have that more variation in my wall thicknesses, which is actually a big no-no when you're designing for regular unreinforced plastics. Normally with those you want to keep some consistent wall thickness, but here you can actually get some variation, which I'll get into later. Another point is injection molding cycle times are much shorter than any machining times you're going to get. That way you can crank out products at short notice a lot more quickly for your market. And then there's assembly part, consolidation. This is nice because you can start consolidating all these metal parts, as Greg said earlier, into one injection molded part. That saves you time, labor, adhesive problems, and all that. I'll get into that in more detail later on. Then you have conductivity manipulation. If you want to be electrically insulative, you can use long glass fiber. But if you want to actually conduct electricity, you can use long carbon fiber, which also means it's very useful for EMI shielding. And then as you vary the different amounts of carbon fiber by percent, you can get more and more EMI shielding. And the longer fibers really provide that network of intermingling fibers so that they can provide that shielding more effectively as well. Then you have lower thermal conductivity. A lot of clients like this because, let's say on a cold day, if they're touching the material, they don't want metal there absorbing all of their heat and making them feel cold. So there's another place where resins help out. Then you have the molded-in colorability. When you're using glass, you can start coloring these structural parts differently, which can help with a lot of processes, especially in manufacturing, but also in cosmetics to make clients aesthetically appreciate your product more. Then you have corrosion resistance, so that way you're not getting rust and other corrosions that you see in metals. I get asked a question very often when it comes to threading. How strong is the threading? Do you have to insert mold threads, or can you directly tap the material? Another thing that I like about our material, or just long fibers in general, is that they make the product a lot more machinable. So you're not going to get the melting as you machine the metal. It actually machines very similarly to aluminum. So in doing so, you can actually directly tap holes and get very strong structure out of them. A few of these, as we have examples on this page, 50% glass fiber showing pull-out strengths that are close to 2,440 pounds. Of course, this is going to vary with whatever your threading geometry is. If you have a wider bolt, you're going to get more strength because there's more interfacial area. But then with 40% long carbon fiber, you're getting pull-out strengths of up to around 3,116 pounds. So that's quite significant and usually more than our clients ever need. So that option's available too. And along that point, just machining a part, post-opping a part in general is a strong freedom that can let you get away with a lot more in the design process. Another thing is, if you do want a sonic weld, the material is quite friendly for that as well. We see this typically happen more when it comes to sonic welded inserts, just because there's a lot of wear if a part is disassembled and reassembled quite frequently. Another thought is if you have wear surfaces that you would rather be more similar to a metal, you can insert mold whatever geometries you want for those wear surfaces. So the image on the right is actually an example of a bicycle link that sees a lot of wear. So the client preferred to just insert mold those components to avoid any concerns. So back to the part consolidation. Each red dot in the image below shows a different component that was able to be consolidated into the one part. So as you can see, a lot of these have 4 dots or 3 dots or 2 dots, all being different amounts of parts that were consolidated. Now this is very nice for clients because it reduces labor costs, shorten production times, eliminate fasteners and adhesives, and there's just fewer defects because there's less human error. And you don't have to ship a bunch of parts from different locations, which saves money again. Now, back to that point about having that variable thickness freedom. So we actually recommend not going below 60 or 65 thou and not going above ½ an inch. Now, that's a lot of design freedom. Now, there are downsides to going on the two ends of these thicknesses. Once you start getting very thin, you're going to want to use less fiber so that you're not ripping up the fibers and so that you're not getting short shots if you have a large flow length. Now, once you start getting to a ½ inch, you also want to consider that you're going to have really long cycle times as you need to cool that much material. But the point is that you actually have that freedom. That's something that you can do with this material that you can't do with an unfilled resin. Now, we typically recommend something closer to an 1/8 inch of thickness. That ensures better flow, less fiber breakdown. But many times when I'm designing, I'll use 200 thou of an inch, and that's useful if I need to get a little bit more structure in some areas, or maybe a fillet will extend the thickness of a region. But when you start getting over 200 thou of an inch, you start losing some of the fiber orientation, which I'll get into later. But now for these images on the bottom left, you can see a little bit of a sink behaving in this component. Now, just to give you a heads up, the thickness of that component was over a ½ inch. And we actually put some glass fiber, low glass fiber content in that, about 20 or 30%. And you're seeing a little bit of sink in that very thick part. Now, we actually use another high fiber content, which is shown in the image to the right, and that's more of a 50% loading, and you don't see any sink in that at all. So that, once again, that gives a lot of freedom. You don't have to worry about ribs causing sink marks and cosmetic issues on the opposing surface. Now, a question that I get asked often is, when we're trying to avoid creep in our design, what should we design for? And usually you want to be able to design as an expectation on your part to see half the max load of the material. That way you're avoiding creep, and the part's going to cycle longer in its life period. Now, other things you want to keep in mind are fiber orientation, which once again is very controlled by gate location, part geometry, and wall thickness. Now, to get into that detail, people ask me, how do you manipulate a weld line's location? Or how do you also manipulate fiber orientation? That's done so by actually manipulating what typical resins consider a downside to designing with plastics, and that's race tracking. But for us, we can actually use that ability, and I better define race tracking. Race tracking is actually when you see higher speeds through different thicknesses of your part, and that's just because, kind of like a pipe with flowing water, the wider the pipe, the more flow you're going to get. That's, once again, an oversimplification, but it's a nice way to think about it when you're designing. So if you want to align fibers, you want them to travel faster in those locations, and then you'll get fiber alignment in the direction of flow. Now, I understand that's a little bit intimidating. That might be like I'm speaking an alien language to you, but don't worry about that. We can actually help you out, and that's why my whole department exists. So feel free to ask questions about that or contact us, and we'll help you out with those details. And I'll get into this later, but we'll also help you with simulations so you can see exactly what's happening. Now, I do want to stress that fiber orientation plays a large role in the structural capability of the part. Not as large of a role as a weld line, but still, it's important to make sure you have fiber orientation where it counts. Now, speaking of fiber orientation, here's a component that we learned a great lesson from. Now, just to give you a summary on this part, this was a connecting rod for a small combustion engine. So we needed that tensile and compression strength along with the stiffness for the engine to keep time. Now, you can actually see the fiber orientation through this breakpoint. Now, we broke both in the middle so that you can actually see the fiber orientation where it counted, which was the middle. Now, I depict excellent fiber orientation with green dots, decent fiber orientation with orange dots or yellow, and then poor fiber orientation with red dots. Now, when this product started, it was more of a beefy brick kind of geometry, and we were seeing failures earlier than we wanted to, and when we broke it open, we saw why. Now, this thicker wall was actually hurting the fiber orientation. I've noticed that the thicker the wall gets, the less fiber-oriented surface you have. So on the image on the top left, you see very little of that interfacial area had excellent fiber orientation, and a lot more had decent or poor fiber orientation. So for us to solve this, we thought the easiest first trial would be to core it out, or give it more of a rib structure. That way we actually have more interfacial area, less thick sections, and then you get what we see on the right. Now you see a lot more excellent fiber orientation and a lot less poor fiber orientation. Meanwhile, the part got lighter, it got more efficient, it got more cost effective, and it had shorter cycle times because it had less thickness to cool through. So that was a win in every direction for that client, and they appreciated that. Now, I threw this image on here, which is a little bit strange, but I find it very fascinating. Now, this is carbon fiber being primed into injection press. So the way we achieved this was by having an unfilled resin that's clear, and then priming in a carbon-filled resin. So now you can actually see the fibers, which are about 7 to 14 microns thick, making their weaved network as they're entering a part. And that's critical for what gives it that structural capability and that impact resistance. Now, talking about the fiber orientation, here's an image that was familiar from what Greg was pointing out, but I wanted to zoom in and spend a little bit more time on some of these details. On the top left, you see that image, a zoom in of how the fiber actually lays itself out. It's not very oriented, but that's actually good because that way it can dissipate the energy in different directions. Now, here's where long fiber is really getting its strength. It's because it's able to network over a longer distance across more fibers, being able to distribute that load to the surrounding neighbor fibers. Now, if we look a little bit lower, you see that black and white picture, and that's an image demonstrating what the pull-out interface looks like. So, kind of like when you're thinking about rebar in cement, You don't have short rebar. No one actually uses that. That's because you need longer rebar to reinforce that cement. So it's a similar concept. For this interface to break, it has to pull a long fiber out further through that resin matrix, which is what's giving it that additional strength and durability. Now, when it comes to a few design details that I also like, you can see that there's very thick bosses on this part, which normally for plastics is a big no-no, because then you're having a variable wall thickness which can cause sink and other visual defects and maybe voids. But here, since the fiber is taking up that volume, you can actually get away with that without actually getting that sink or other defect, which is giving you an overall more robust geometry. When we look at the center of the part, you can see that more intricate detail, very thin walls that the fiber's flowing through. Now you can do this as long as you have shorter flow lengths. You wouldn't want to do this over a very long flow length or you'll start breaking down the fiber. But when you have smaller details like this, you can still get away with it and still have a robust part. Something that you really want to keep in mind when designing and you're looking at our data sheets that are online and you're seeing all these strengths characteristics for each material are they're coming from ASTM standards. And those standards dictate that you're going to use very common geometries like a tensile dog bone sample. Also keeping in mind when we're injection molding these, obviously flow is going from one side of the dog bone to the other, and that's producing about an 80% alignment of fiber. So when we're doing all that tensile testing and we're reporting those numbers, keep in mind that in a dog bone there are higher orientations occurring in there giving it some strength. So if you have a geometry that is going to be less simple, you want to keep that in mind. If you have a location that's going to have poor fiber orientation, you probably won't get those strengths. So that's where we can come in and help you simulate what your fiber orientation may be like in that zone. Now also I want to report, which I did earlier, that you're going to, when you have thicker walls, you're going to have less orientation as well, and that recommendation for thickness was demonstrated earlier and you can look back at that whenever you want. So now the importance of design. It's very key that you don't just depend on the material for strength. You also want to think about how you can use reinforcing geometry to do that. Now, once again, I said it's actually cheaper instead of having to machine out ribs when you're dealing with a mold, because then you can just mold in those ribs because the tool is there constantly with those details. Now, I want to show you just how powerful that design can actually be. So the tray on the left doesn't have ribs, and the tray on the right does, obviously. But now when we look at a long glass fiber 40% PA66 without the ribs, it comes in at a weight about 10.1 ounces. And it was able to, under compression, handle 985 pounds. Now, on the tray on the right that has the ribs, came in at a weight at 11.4 ounces. But it was able to carry 10,252 pounds. So for such a small difference in volume, you're getting huge strength increases. Now, let's carry that over to carbon. When this same design was filled with carbon fiber, it came in at a weight of 9.2. So it gets that competitive edge in weight. And the unribbed was able to handle 2,055 pounds of load, which is good. But when we actually added the ribs, it came in at a weight of 10.4 and was able to carry 14,691 pounds. So it really pays to have a design that fully utilizes the molding process and the material. Now, other things to keep in mind is gating. Like I said before, where you position the gate will influence fiber orientation at different locations in your part. Now, typically, the industry for unfilled materials uses a gate size known as a pin gate, which is 1 millimeter by 1 millimeter approximately. Now, we discourage that because when you have a gate like that, you rip up your long fiber due to the shear forces and the high speeds of flow in that location. And you don't want to rip up the long fiber because then you turn it into short fiber, which is going to make it a weaker product. So we suggest using larger gates that enhance flow, minimize shear in that location, and then to post-op remove those gates afterwards. So you want to keep in mind you're going to want to keep the gates in lower cosmetic areas. You also want to keep in mind what your runner system will look like as well as gate. So when it comes down to our tensile bars, for instance, we use fan gates, and our runner system doesn't take any sharp corners. We're trying to, again, not incorporate sharp corners because we don't want to reduce the fiber length. So we add fillets and bends to that system instead of sharp transitions. Now, I get questions about auto-degating often as well. Can you auto-degate? Yes, you can. But keep in mind, because there's long fiber, you're going to have some of that interfacial pullout, which isn't always going to be pretty at that location. So make sure if you're going to do auto-degating, you have it in a non-cosmetic location. Now, as I said earlier, we offer a lot of simulation help. We understand how intimidating it can be to design with a new material, especially if you're used to machined aluminums or steel. That's where we can come in and make that a little less stressful for you, because we have a lot of experience under our belt with that. So a few of the simulations that you can expect that we can help with would be mold flow injection simulation. And once again, we can have a video conference with you or make a PowerPoint or anything to demonstrate the details, concern areas of any of these simulations. Other simulations include fiber orientation, which was key to the strength, finite element stress analysis, so that we can figure out which locations we need to be more concerned about and reinforce. You have finite element deflection analysis. Maybe the product that you have can only deflect so much before it's out of spec for the function. And we can also start simulating warpage for you so that you know maybe what the molding process could do to the product and its dimensional accuracies coming out of the mold. We can also render the product as well. Now, this is key for a lot of clients who need to pass their product through marketing, and they need to accept its looks, they need to understand what its cosmetics may look like. So we can render that for you as well. Now, typically, clients want to know how do they interact with us and what can we do for them right up front. Now, we like to get into a design process as early as possible so that you're not too far down the road or have to make a lot of changes and waste time in your design process. So once you have a concept, you can either send us a picture or a drawing, but it's a lot more useful if you already have a CAD of your concept, and that'll make things a lot faster. So you can send us that CAD, we'll review it for moldability, for fiber, for whatever material we want to select for this, and also let us know what the loading conditions are like. So even though your part may be moldable, we can also suggest different changes you can make to make the mold production a little less costly for you as well. But once you give us these loading conditions, we can also run a finite element analysis on it. Once again, pointing out those highly stressed areas and how we would suggest avoiding them or how to reinforce them. And also, in parallel, we'll be running a mold flow. So we can see where the weld lines are, where your fiber orientation is good or poor, and we'll make sure that places where you have a weld line don't sync up with places that you have your highest stresses. And if they do, we'll come up with creative solutions for moving those weld lines so they're no longer in your highest stress locations. We have a lot of experience with that, so feel free to ask for help with that. So kind of just as a summary of our part, we will take you from concept to production and everything in between, giving you warnings of what may be a concern, what won't be, and just give you simple tips of how to tune that process. So we'll be looking at your concept, what material formulation, and running through those analyses with you, and maybe even linking you up to somebody who can produce it if you would rather have your own molder. But we can also do that in-house as well if that makes it easier, especially during prototyping.